we just start with a reminder of what we did last class, where we are using this new library called Pandas. And this data set that we found online, we saw with this command head, which is, as I was saying, a terminal command, or shell command is another way of saying the same thing. This is not Python. This is something of the operating system, but it allows us to just peek into the file before we do anything with it, just confirm that this is what we want. We can see from that peeking into the file that we have comma separated values. That's what the extension CSV means, comma separated values. And we have in the first row something different than all of the other rows, and those are the labels of the columns. By using pandas.readCSV, this command, and there are many commands, many read commands in Pandas. You can read an Excel file, you can read various other types of files with the various read commands, and this reads the file and then turns that into a data frame. This variable beers we created is, as we see with the type command, is a data frame. And this data frame, what it is that you save a whole table of data into one variable, and that table of data has labels for the columns, and we can get that from using dot columns, and we have row indices, okay? And just one column of that data frame is called a series, and a series is a single column with the index. So it's not like an array because we have the indices now, and the indices mean something, but we can turn it into an array, as we learned by using the dot values attribute. So let me go back to my Jupyter Notebook. So we learned this very important feature of Pandas data frames, which is that we can access the data using the labels. This is pretty amazing and gives you so much flexibility. You can access here the column. Remember here from printing out the data frame that we had these labels here. ABV corresponds to the alcohol by volume measure for these different beers. And we use the label to grab the whole column there. The column is a series, as I just showed in the slide. And so it consists of the column with its label. So if I grab the first 5 rows, I can see the index and the value. So we learned how to extract columns from a data frame using the label. And then we used this very important command of Pandas that removes the empty values. A typical thing that happens when you're working with data is that you may have incomplete data. Not all of the rows and columns are complete with a value that is meaningful. And those could be empty, or you could have something that says not a number, NaN. And this removes all of that. And in this case, what we were trying to do is save only the rows that have meaningful values. And we saw here, comparing the lengths, that we lose quite a few rows when we look at the ABV column, but many more when we look at another column, the IBU column. So we got it to that point. And so I'll start a new Jupyter Notebook. We don't need to re-download the data, of course. So let me just call this, I guess, class 13 notes, and we will repeat some of the steps from before, but I'm going to cheat a little bit by maybe copying some things. So let's leave some notes for the human in the future, ourselves, when we come back to this class 13 notes, continue lesson 1 of EngComp 2. I'm going to use underdash for italics. Okay. And as always, import NumPy, our favorite library for engineers. Import Pandas gives us all the Pandas goodness of being able to work with data frames. So we're going to read the data again. So let's just quickly retrace our step. Beers is the name of the variable, and I'm going to use pandas.read _CSV with the name of the file. We know that the file is beers.csv because that's how we brought it from the internet. And beers, how about if we look at beers.columns? What does that give us? Oh, okay, here we see the list of labels of the columns, right? This is what I showed you in the slide. Dot columns is an attribute of the data frame that we can extract. and display there. So the other thing that we did then is to extract, now that we're looking at the names of the columns, these are the names that we can use to access the data. Those are the labels. And so we can extract the column ABV using the label. We're going to save that into a new variable, ABV series. Always name your variables things that are meaningful to understand what they are. So this is the series, and I obtained the series by accessing with the square brackets like we do indexing and slicing, but instead of an index, I give it the label. ABV is a label, and I execute that. Now we have a new variable, ABV series. So len, I can use len. Len is a Python function that you can use on anything almost. ABV series, it says 2,410 entries. But we know, we observed this data before. We know that it has a lot of empty values. So we create a new one, ABV _clean, we call it that. Clean data, we always, it's customary to say that the act of getting rid of things you don't want in your data is to clean the data. And what we're going to do is apply on ABV series the drop NA method. So we have the round brackets here to apply that function onto ABV series. So we have a new variable now, ABV clean. Let's check its length. Okay, so we lost, as you can see, a bunch of rows that had not A numbers there. And now the other thing that we do, and I'm going to add a comment here, is extract the values into a NumPy array. And why do I clarify that? The reason that I clarify that is that this series is the column plus the indices of every row entry. And so if I just want the values, I can extract them into a NumPy array using ABV. I'm going to call it now just ABV with nothing more. ABV _clean dot values. Okay, important to notice here that dot values, like up here, dot columns, we don't use parentheses because this is considered like a property of that data type, right? Dot columns is a property of any data frame. Dot values is the property of a series. And it's, by the way, it returns a NumPy array. So let's just check that type, ABV, it's a NumPy array. So now we can do calculations on that. We could always do calculations on the series, but we'll learn to do that later. And let's do the same for the, going back here, I show you there's the column label IBU. We're going to do the same thing, and let's do it all in one go. IBU series is beers. We access beers with the IBU label. Okay, now we got the column. We know it's got a lot of empty values. So let's create IBU clean as IBU series with drop NA. So that gets rid of all the empty values. And let's add the step now to get the values of the clean version of the column IBU with IBU clean dot values. Maybe I'm going to print the length as well, just for kicks here. So len IBU series, and let's execute that. Error. What happened? Oh, beers with an S. That's how I named my Pandas data frame. And there we are. It doesn't print here as I expected. I'm going to put it at the end. There it is. And now I'm going to print also the IBU clean to inspect that and inform ourselves that we lost a lot of values. We lost 1,000 values there. There's a lot of missing information in that column. And we had an exercise at the end of last class for writing a function to compute the percentage of missing values. Obviously, I could compute that percentage for the particular value of the IBU column, but what we wanted is a function that can receive as an argument the Pandas series, and internally to the function compute the lengths, compute the drop NA, and get the values and compute the percentage. Okay, so that the idea was that if you write a function, it should be general to be used with any series. And you notice here from comparing output 12 and output 13 that about 40% of the data is missing. for IBU. And this is important to notice because whenever we calculate statistics on this property, we have to keep in mind that because we have so much missing data, that the statistics could be biased in some way. It could be that this statistic is particularly missing for a category of the canned beers in the set or something like that. So that's something to always keep in mind. Okay, so now we're going to compute some statistics on these. We're going to learn to do some what's called exploratory data analysis. And we're going to focus first on the numerical values of these properties of the data set of beers, the ABV and IBU. So let me create a subheading here. And I'm going to call it exploratory data analysis. And what are we going to look at first? I'm going to look first at the minimum and maximum values. And we're going to use for now NumPy on this. And well, NumPy, of course, has the functions to compute that. And we could just, it's what you would expect, NumPy.min and NumPy.max. So let's save those values for the ABV data. ABV min, this is just going to be a number. By applying numpy.min on the ABV column, I'm going to do the same for the maximum value, numpy.max. And those values now are saved into two nice functions. But of course, if I execute that, I don't see anything because the important thing that happened there is the assignment. Let me highlight the cursor. The assignment was the important thing that happened in input line 14. And now I'm going to print that for the human to read using a print command with a message. The minimum value for ABV is, and then I'm going to print the value ABV min, and I'm going to add print the maximum. So just showing how you might want to print the values that you computed in a way that is human readable. That message now is human readable. You have an explanation of the numbers. You don't just print the number, and that's good practice as well for your programs. Let's do the same thing for IBU, numpy.min, IBU. We're working with NumPy arrays now. We extracted the data in a NumPy array, and I could print it, and I could do this in the same line. I don't need to do a separate line now. I'm going to cheat, and I'm going to copy and paste here to save some typing. Now, all of these copy and paste type of operations are always quite tricky because notice here I need to remember to change the value. I see where I have to change, and because this is structured here, it's not so risky, but always be wary of your copy and paste. You save typing, but can introduce bugs, so you have to be careful with that. Okay, there we have it. Those are the minimum and maximum values for these two quantities. And well, what would you want to do next? Typically, when you're doing exploratory, with data that is of the numerical type like this, you might want to compute the mean value. So let's do a subheading here for mean value. And so if you recall the formula for the mean value, let me just reload here the class notes. And here is the formula for the mean value right here. It's the sum of all the values divided by the number of samples that we have. NumPy, of course, has a built-in function. We already learned about the NumPy built-in function to compute the mean value in the last lesson when we used it for our formula for regression. So let's now use that again. Okay, mean value. And we're going to compute the mean value and also save those values into a Python variable. So ABV mean _mean is numpy.mean of ABV, and IBU mean is numpy.mean on IBU. Okay, so we've saved the mean values there. And next what we're going to do is going to print those values. Look at what we have over here is a print statement with a message, comma, and the variable, and we get that kind of print statement. But we're going to learn a different kind of print statement now. That is just a little bit more sophisticated, let's say. And so what we're going to do is use one print command, and we're going to put one message and print both the mean values inside a sentence. So how do we do that? We create the message, the mean values for ABV. So no, let me do it the following way. The mean value for ABV is Okay, and I want the actual value. I want the actual value to be printed there in the sentence. And so I'm going to use two curly brackets, empty curly brackets in there. And then I'm going to continue the sentence right after that. And for IBU is, and again there, I'm going to put two empty curly brackets. Okay. And those are the locations where I want the variables to appear. And so what do we need to do for Python to give me that? After the string, which is between quotes, I use dot format, and as an argument to the dot format function, I give it the variables that I want to appear in the position of those placeholders that I left with the curly braces. So ABV mean, comma, IBU mean, those are the two variables, the two Python variables, and dot format is going to insert those values inside those brackets. So let's execute that and see how it comes out. You see now I have a full message, a full sentence with the values inserted there in the middle. Now, okay, that's kind of what we wanted. But one thing that's not very nice of that is that you get all of these ugly, very long numbers. So normally what you want to do is print fewer decimal digits so that the sentence is more readable for the human. So let me select all of this again, because I'm going to redo it. I'm going to copy that and paste it here. But instead of having the empty brackets, now we can give it some syntax here that indicates the number of digits that we want for the variable that is going to be printed. So we use :.2f, that's going to be 2 decimal places, and :.2f for 2 decimal places. Did I get rid of a parentheses there? I think I did somehow. Yes. Okay, there we go. So my copy paste kung fu went wrong here because I did not select the whole sentence. As you can see, we do have at the very end of this line the 2 parentheses that we need to close. So that looks a lot better, doesn't it? This is a sentence with the actual values of the Python variables inserted there in the middle. And many times we want programs to output some messages for the user in this way. So inside the curly brackets, the curly brackets are like the placeholders for where we want the print message to insert the variables. If we don't put anything, the whole value is printed, but then we have some syntax to indicate the number of digits after the decimal dot here. And this type of formatted print message has this specification for how to show the values. And really the only way to learn how to do this is called string formatting is whenever you have to do something like this, you look it up, and eventually when you do it enough, you learn it. So we did leave in the lesson a link to material. So let me now go back here to the lesson. When we show you this in the written out lesson, there is a link to the Python string format cookbook with lots of tricks to get your print messages just right. That's string formatted print statements. Another trick for your arsenal. So now let's learn about variance and standard deviation, which we haven't used before. And all right, when you are doing exploratory data analysis, these are the very typical things that you want to compute with numerical data, right? The mean and so on. There are two different qualities of the data that we look at here. The mean gives you a sense of the center, where the center of the data is, and the variance and standard deviation give you a sense of what is the variability of that data. So there are different qualities that these numbers represent, and they're both important to understand your data. Another way that we could imagine describing the spread of the data could be the difference between the maximum and minimum, right? That gives you an idea as well. We call that the range of the data, the difference between maximum and minimum. But variance and standard deviation give you a little bit of a different view on the spread. So let's just leave a note here. The mean gives you an idea of where's the center of your data, and the variance or standard deviation tell you about the spread of the data. Again, let me just rewrite that. All right. Now, I have also added here in the lessons a link to a video on YouTube. Let's see if it's still alive, this video, because sometimes things are taken down. Yep, it seems to be still there. Okay, so this is a video from a Stanford course on statistics, and I find it very, very good. And so I shared this with you, and I really recommend that you watch it. You might think that variance and standard deviation are very simple things, but there's a few little tricks. Let's use our written out lesson here to review this. The distance from the mean, suppose that we use xi to denote all our data values and x bar to denote the mean, the distance from the mean is going to be xi minus x bar. If we were to think about taking the average of the distance from the mean, the problem with that is that some of those distances are going to be positive and some are going to be negative. And so if I average them out, you get close to zero. So it doesn't quite work. The way to usually get rid of the pesky negative values in our formulas is to take the square. So that's what we do. We take the square of all of the distances from the mean. We add those up and divide by the number of values. Now, there's a very important distinction to make in statistics between the variance and the standard deviation of a sample and a full population. And this is a little bit technical. And Professor Zainani, in her video that I recommend, discusses this. And we have a short explanation in our lesson. When you are taking the variance or standard deviation of a full population, you use this formula that you are used to with 1 over n. But when you have a sample of that population, then there's a bit of a change here. Instead of having 1 over n, have 1 over n minus 1. Professor Zainani explains this very well. Some people explain it as you lose a degree of freedom. You have some bias when you only have a small sample in your data. I will leave you with the recommendation of both reading the explanation that we have in the lesson and watching, it's a very short video, 7 minutes or something, the video from Professor Zainani about this. The important thing is that when we compute this in Python, we need to remember which case we are looking at. Is it a sample or is it a full population? Now, if we go back to our data, we know that we have 2,400 or something beers. We don't know. We don't really know if these are all the beers or it's a sample. We just have to assume that it's a sample because it would be very hard for someone to collect the data for every single and all of the population of craft beers available. So we have to assume it's a sample, and therefore we have to use the sample, standard deviation, and variance. And that is the trick here, to remember that we are, in this case, using a sample. Okay, so now that we have that technicality sorted out, let's do a little bit of coding to compute the variance of our data. So to start with, we will create a function to compute the variance of an array, a data that comes in as an array. Let me add a few lines of a few cells so I can scroll up a little bit here. All right, so let's start with creating a function. I am going to call it sample var for variance, and I'm going to assume that it receives an array as input. And notice I've used in the name of the function already something that indicates the meaning. We're going to use the formula for the sample variance and not for the population. Let's use the 3 quotes to denote our doc string, which means the instructions of use for this function that we're creating. And first we say what it does, calculate the sample variance of data. Let's keep it simple. And let's say what are the arguments. I'm going to reduce the number of lines here just to make it take less space. Array, well, it's called an array, and it is an array. And we say that it contains the sample of values. And what does the function need to return? It's going to return, let's use var for variance, and it's going to be a float. We like to usually indicate the type of the return value just to have more information. And it's the variance of the sample. Now that we have that information available, writing the doc strings has actually helped us think through what the function does. And now we're going to write the function. So we need to compute the sum of squares. So remember the formula here, the sum of squares. Well, that's the standard deviation. But for the variance, we have the sum of squares first, and then we are going to have to divide by 1 over n minus 1 because it's a sample, not a population. So let's create a variable where we're going to accumulate the sum of squares, and I'm going to use sum under dash sqr for this variable that I'm going to initialize to 0, and then I'm going to be adding the values inside a for loop. We also are going to need the mean to compute. Remember, in the formula we have these differences, right? Distance to the mean, the difference between every data point to the mean. So we need to compute mean. So let's say the mean is going to be numpy.mean of what? Well, of the array that comes in as an argument. Okay, now we have the materials we need to compute things, and we're going to go into a for loop, and I'm going to iterate through every element in the array. So I'm going to use for element in array, using, of course, variable names that are useful to us humans. And then what are we going to do here? We're going to accumulate the sum of squares there in this variable. So I could do sum of squares equal the previous value of sum of squares, right? Plus what? Well, we want to add element minus mean and take the power 2 of that. But if you look at this thing here, whenever you have this pattern of on the assignment, we're assigning the previous value of the same variable and adding something to sort of accumulate there. Whenever you have that, you can replace all of this thing between the plus and the equal sign by plus equal. And that is a trick that many languages have for simplifying the statement of accumulating. Well, I didn't want to execute that yet, but I'm going to edit it. I could call this X. And it would be the same thing. This is simply a placeholder for well, I have to change it to X there too. This is the placeholder for the argument that is going to come in here. I could call it arg. And it would be the same thing. I have to remember that I'm consistent, that this is always the variable name that inside the function represents the input that came in when we call the function. When you call the function for the first time, I am going to call it with something that exists as a variable name there. And I'm going to call it in the next line after I define it, sample mean, but I'm going to call it with something, for example, ABV, something that is a Python variable that already has been defined and contains an array. I've said this is an array, and so I am going to have to send in an array. At this point on this line is where we execute the code that is inside the function for the first time, and this array ABV comes in here. It changes name, and then out comes the output result of the function. Now I've changed the name. I'm going to call it arg for argument. So I need to change that name. Now I have the value of the length that appears in the function. That's n, right? In the function, that is the variance of that is the formula for the variance for a population. But for a sample, I need to do n minus 1 in the formula. So now that I have n inside the function, I can compute the variance. The variance is going to be this sum of squares divided by n minus 1, because I've said here in the name of the function, it's implied sample variance. In the docstring, it says it's a sample. And so I need to use n minus 1. Now that we've computed that, I can return the variance. And now when I execute that, notice I've executed input line 23. What input line 23 has done is define the function, but none of this code has been executed until I call it, and I'm calling it here with the ABV values, for example, and I obtain VAR. Now, I have an exercise, so I'm going to leave this up, and I'm going to use the timer, taking my camera off and put the timer behind there. And the exercise is the following. You now are going to modify the function or rewrite this function in a new, you can rewrite it in a new cell or just modify it in place. And instead of doing the for loop that I've shown here, you're going to use the numpy.sum. So exercise, rewrite the function using numpy.sum instead of the loop. Okay, there we go. Important to note here that I kind of wrote a function in a non-Pythonic way because I'm using a for loop to sum the elements of an array when numpy.sum does it in one line. So this is very important to remember whenever you're doing something like a for loop into the elements of an array. Ask yourself, well, NumPy should provide a function to do this, and look it up, because usually the answer is yes. And you can save from writing all of these for loops. So now we have the sample variance. And so to compute the standard deviation, we take the square root of that. So let's define a new function and call it sample standard deviation. Usually is abbreviated STD. And now we're going to use array here, but I think array was confusing. I'm going to use arg again. I like that better now. It was confusing because it is a type. And this is going to be 1, 2, 3. 3 quotes to leave a doc string, computes the standard deviation of a sample from a population, okay? And the arguments, just one argument in this case, is arg, and this is an array and contains the sample of values. And it returns, what does this function returns? Well, we want to return the standard deviation. That's going to be just a float. Okay, so there is our doc string. And I recommend always to start by writing the doc strings of your function, because this tells you what you want the function to do. And you kind of already think through these steps here by just writing them out. So in comes the argument, and we could do the whole set of steps to compute the variance and then take the square root and return that. But we don't need to do that because we already have the variance. And so why don't we just compute the standard deviation as the numpy dot square root of what? Well, we already have functions. So the sum function sample variance can be called from inside this other function, and it's like composition of functions in mathematics, right? And we save ourselves from writing all of that again, especially if you've already written that function and you already tested it and you know that it works and it gives you the right answer, then why write that code again, introducing opportunities for bugs? So now we have that, and we return that value so that we can have it available to the rest of our code. So now we can compute ABV standard deviation using sample._std for standard deviation ABV, and the same for the IBU standard deviation. And we call it sample to be specific that we are using that 1/n-1 in the formula, which corresponds to sample. And now we can do a print statement, a fancy print statement that we just learned to do with string formatting. The standard deviation for ABV is, and now I'm going to do the curly braces to introduce the placeholder, and inside the curly braces I'm going to indicate we use :f for f or 2f, 2f is to 2f, two decimal places seem enough. And for IBU is curly brackets again, :2f. And okay, so now that we have that string there with the message and the placeholders for where we want the variables, we do dot format, and we input to dot format the variables that we want printed there: ABV standard deviation and IBU standard deviation. And let's execute that to see how it comes out. And you see we get a nice message with the variable values in the middle there, and already rounded off to 2 decimal places, which we decided was, of course, we can change that to 3. Suppose that this value now, I want that with 3 decimal places because this is a more sensitive measure, and why not? We could use different values for the two. That is standard deviations and variance. But guess what? NumPy has a built-in function to compute standard deviation and variance. So we didn't need to go through so much work and write our own functions. And whenever you're again, whenever you're writing some code with NumPy that feels like somebody else might need it, look up the possibility that it's available. It's probably the case that the function is available in the NumPy library. Okay, so I'm going to stop there today for today's class, playing around with some statistics with this data set.